This is the final video in our review. This is the chapter 6, fatigue failure resulting from variable loading. We've talked about it. You haven't done any homework on it, so I'm going to ask at most more qualitative kinds of questions, not quantitative kinds of questions. And so there's some general discussion of fatigue. We talked about the rotating beam specimen being a very specially made test specimen, and it is called the rotating beam because we will support this as a cantilever at one end, and we will place a moment at the other end, and that'll cause a bending stress, but at the same time we're loading it, we're going to rotate it so that the stress goes from high to zero to negative, back to zero, back to high on every part of the every piece of material in here. As the beam rotates, we'll go from positive stress to negative stress. So here's where our fatigue data will come from. And then we have to make judgments on our part, which is going to have totally different shape, totally different surface finish, totally different kinds of loading. Yet we still have to use this data to make some decision about whether our part will succeed or fail. If we plot the rotating beam test for various size loads, extremely high loads, because this is our loading axis, will fail after a very small number of rotations of the beam. Okay, so this is a graph of fatigue strength versus number of cycles to failure. This is the S-axis, this is the N-axis, and this is called the SN diagram. And from the SN diagram, once we have the diagram composed of data from lots of experiments done on our particular material, we can see the low cycle region, a kink that sort of transitions to the high cycle region. And if we're talking about steels, then we'll see another turn in the curve where it goes flat. And at this stress level, we've reached our endurance limit, which on this one we would read as a value of 50. Okay, and our endurance limit typically happens at 1 million cycles. So if steel materials last to 1 million cycles, they're probably going to last forever. And we'll often take advantage of that idea and try to design steel parts to have infinite life in fatigue, if that's appropriate. So this is the SN diagram. What might I ask you to do with this? I might give you an SN diagram and simply say what kind of stress level can we apply if we want to live 10 to the 5th cycles. Well, there's 10 to the 5th cycles, and we'd read across. If that's a 50, that looks like to be about a 60 or so. And so about 60 kpsi of rotating beam loading, which is fully reversed loading. It's positive, it's gone, it's negative, it's gone, it's positive. Fully reversed loading looks like a typical sine curve, is what the SN diagram applies to. Then we said, let's move on a little bit. Move on a lot. Or did I miss it? No, I'm sure I didn't. Okay. We said that more often than not, the real kind of stress loading that we have over time is not the fully reversed, but it's a more general fluctuating kind of stress. Okay, where here are some samples of fluctuating stress. Here, here, and they're not necessarily some sinusoid. We may have this combined with that over time. We could have any kind of loading that we can physically reproduce over time. If we just move over here and represent our nominal loading as a sine curve, we would see this kind of loading, which is symmetric about the zero axis. So our load does start at zero, it goes positive, negative, positive, negative. This is the fully reversed loading, and this is what the SN diagram applies to. If we take this loading and shift the load upward so that the bottom of the curve rests on the zero axis, then that's what we have right here, which means our loading goes from high to nothing, high to nothing. This can be called a repeated load. The load is there, the load is gone. The load is there, the load is gone. SN diagrams do not tell us about failures directly of this kind of loading. And then the more general kind of loading would be a high stress, a low stress, a high stress, a low stress. And what we said was we can characterize this kind of stress loading by a mean value of the stress, the symmetric axis of the sine curve. So a mean value of the stress as measured from zero, and an amplitude value of the stress. And we have to be careful with our definition here because amplitude is not peak to peak. Our amplitude is peak to mid. Okay, and so half of the peak to peak loading would give us our amplitude. So if we have an amplitude of something and a mean of zero, what kind of stress loading do we have? Amplitude of something, mean value of zero right here would be the fully reversed loading. If we have an amplitude that is equal to the mean, the amplitude is half the load, the mean is half of the peak-to-peak load, then that would be the repeated loading. And we'll see how this appears on a new diagram, the Gerber or Goodman diagrams, in just a minute. And then when we have a amplitude that is in no way really related to the mean, then we have our general type of fluctuating loading. How do we handle fluctuating loading since it is not handled by the SN diagram? We go to, and this is very messy, we go to a diagram, and obviously there are lots of different theories on how these kind of things fail, but the key is we go to a diagram where we plot mean stresses on the x-axis, and we plot alternating or the amplitude stresses on the y-axis. And then here's the logic. I repeated this in class, but here's the logic on how these diagrams work. I want to focus specifically on this straight line. And notice this straight line goes through the ultimate stress on the mean axis, and this straight line goes through the endurance limit, which we read off the SN diagram on this axis. This SE is a failure boundary on the vertical axis, and this line, called the Goodman line, is a failure boundary on the entire diagram. If we're under this line, we're safe. If we're out beyond this line, out here, then we're going to fail in fatigue, according to this theory. How does this line come about? It says, let's look at where this line would hit this axis for a certain kind of failure. Let's look at where this line would hit this axis for a certain kind of failure. That gives us 2 points on the line, and with 2 points we can draw the straight line. Living on this axis means we're living at sigma mean equals 0 and sigma amplitude equals something. Well, sigma mean equals 0, sigma amplitude equals something means we're doing fully reversed stresses. Let me remind you of that. Okay, sigma mean equals 0. See that 0 right there? Amplitude equals something. That's fully reversed stresses. Where do we fail if we have fully reversed stresses? We fail, according to the Goodman diagram, if we want it, or according to the SN diagram, if we want infinite life, we fail at our endurance limit. So we'll plot the endurance limit right there, and that gives us 1 point on our Goodman line. Then we move to this axis and say, where do we fail based on what's happening on this axis? Well, if we live on this axis, we have a sigma mean of something, and we have a sigma amplitude of nothing. Let's go back and look at that. Okay, on this stress, this would be a stress that says we have a sigma amplitude of something and a sigma mean of something. If we let this amplitude get smaller and smaller and smaller, our stress state simply becomes a straight line at the mean location. And a straight line at the mean location basically means static loading, no fluctuation left because we send that to 0, static loading of some moderately high value. Where do we fail when we have that kind of static loading? So this axis is the static loading axis. If we live on this axis, if we're a point on this axis, we're a static loading. Well, we fail or break into multiple pieces under static loading when we reach the ultimate tensile stress. So to generate the Goodman line, we draw a line that passes through the endurance limit on this axis and the ultimate tensile stress on this axis. We draw in that straight line, and then we can tell if we're safe or if we're heading toward a failure. And then when we have a load line and a point on the load line, we can then judge factors of safety just like we did with our static failures. So this straight line that passes through endurance limit and ultimate tensile is called the Goodman line, or the modified Goodman line. There's another curve that passes through those same 2 points. Okay, you can see 2 curves passing through that point, called the Gerber line. The Gerber is more accurate, but the Goodman is more conservative. So we have a couple of choices in which theories to use. And in mechanical design too, when we're applying this, we'll more often than not use the Gerber line because it's more accurate. So just like we'll choose quite often the von Mises theory for static failure because it's more accurate. We'll choose the Gerber for fatigue failure because it's more accurate. But the only other thing that I even mentioned was this endurance limit has actually been modified before it gets here because of differences in the part, and I called it the alphabet soup of correction factors. See if I can find that quickly. Here it is. These are the various modification factors that will turn an unmodified endurance limit into a fully modified endurance limit, and this is the number that we take to our Goodman diagram. And that's really all that I've said about fatigue. What might I ask you to do? I might ask you to read an SN diagram, and if I give you a life, you tell me the stress we can apply. If I give you a stress, you can tell me how long that part would live. Or I might ask you to draw a Goodman or Gerber diagram. Let's move on down. We'll get close to that. Here we go. Okay, if I give you the ultimate strength and the endurance limit, I might ask you to draw the Goodman diagram, which is a straight line. Gerber diagram, just draw in a curve. It sort of comes out horizontal here. The parabolic curve that comes out horizontal here and passes through the ultimate tensile stress. So if I gave you that information, I might ask you to draw the diagram. If I gave you a point of sigma A and sigma amplitude and sigma mean, you could plot that point and estimate factor of safety. I might ask you to do that just to show your understanding of this diagram. And that ends our discussion of Chapter 6, and that's the last of the videos. I remind you that because of my recording system, I couldn't grab and copy equations, so I'll have to go back and do that in a second pass. So the equation sheet will come a little bit later than the videos.